Hi, so on this lecture we will very briefly outline how we could generalize our treatment to three-dimensional solids. So here essentially we will speak a little bit about the difference between a local energy band gap and a so-called global energy band gap, and we will basically use an FCC lattice material, so aluminum as an example solid that we already know from like a real life, that the aluminum is a piece of a metal. So this is what we will do in our 2-slide long lecture. So as earlier when we were treating lattice vibrations, phonons, and first we started with a one-dimensional model, and then we generalized, or at least we outlined how this could be generalized into 3D case. We will now do the similar thing, but now instead of lattice vibrations, instead of phonons, we have electrons and their wave functions that we're interested. But the same approach works either way. So in that sense, there's nothing new under the sun or in a piece of a periodic solid. And what we will do, we will very briefly extend the treatment from 1D band structures into a fully three-dimensional band structure. And here again, we will take use in our description these points of high symmetry, also known as the critical points, that are residing inside the first three-dimensional Brillouin zone that we are using to describe our system in the reciprocal lattice. And this, we note that if you're really interested in a more detailed mathematical treatment, please go on, read about Kittel, the later chapters, and you will see how the mathematical treatment goes. But we do not need to go there in our introduction course. That's not the core topic if you want to go through the main concepts associated with periodic structures and solid-state physics. And what we will do here in the upcoming lecture, we will just look into the band structure of aluminum. And this is like a good example as any when we are looking at metals, since at least we know that from like a high school knowledge that aluminum is a metallic solid. And we also know that aluminum, it has the periodic structure based on its FCC lattice structure. So that also simplifies so that we already know the shape of the reciprocal lattice. The first Brillouin zone of the aluminum. So the electronic band structure of aluminum near the gamma points and the X points will be shown in the figure A. And that basically also gives us the first Brillouin zone that will be shown in figure B. And what we see here in the figure, we will see a so-called local band gap in the band structure. And of course, then that would imply, if you have a band structure, a band gap in a band structure, that the material would be a semiconductor or a dielectric if the band gap is large enough. But of course, since we know that aluminum is a metal, so something seems to be highly surprising or weird in our description. So as promised, here in the A figure, I'm showing the 1D dispersion relation. So I'm plotting from the gamma point, from the origo in the first Brillouin zone. From here, I'm first going to the X point, so into this edge in the first Brillouin zone here. So I'm plotting the dispersion relation, what kind of electron states I can have. And I'm plotting here with the Fermi level normalized to be 0. And we can see roughly the kind of energy scale that we have in here, so that the metals, the Fermi level, where it resides with respect to the kind of lowest energy states of the electrons. And then in this part, we are going from X back to the gamma, and this is how we are plotting things. So we just go along this single line. And when we are just looking at this line, it would seem to be that we actually have a band gap in our structure. And this is surprising because if we have a band gap in our structure, in our material, it would imply that this material would not be a metal at all, because there would be this kind of possibilities that the conduction electrons would not be free to move in here because they would be in the valence band. And here, please remember, this is how it looks like. The first Brillouin zone for an FCC lattice. And now I will try my best to clarify what actually happens, because we do know that aluminum is a metal, so that we really plot the full dispersion relation also near the other points of high symmetry, so also nearby the other critical points. And what we see here is that now this band gap that we saw earlier nearby the X point is only a local band gap, and there actually is no global band gap in aluminum. And this is what is important when we try to understand the properties, the electrical properties of metals. So if we want to have a metallic behavior, then we need to have a global band gap in the band structure so that the system could be behaving as a metal. And this is how the full dispersion relation looks like. So now I'm also plotting from the gamma point. Again, I'm going to the X point, but now I'm going from the X point to the W point, and from W I go to K point, and from K point I go to the L point, and from L point I go to the gamma point. And this is how these dispersion relations usually are being plotted. And as we can see here in the X point, what it seemed to be in the earlier figure, a band gap, it was actually just a local band gap. And now where we are at the Fermi level here, we see that there actually is no band gap taking place in here anywhere. So this is actually now we see straight on that aluminum doesn't have band gaps actually. No complete band gaps exist, and thus it should be metal. And it is indeed a metal, as we know. So that's nice. This is a very brief way of showing how the treatment would be generalized. And of course, I'm cheating here because I do not really go into the ugly details and other examples of mathematics, of other kinds of structures. But hopefully at least you can appreciate how things could be generalized when we would go to three-dimensional structures. But for simplicity, I feel that this is enough, and we don't really need to go into the ugly details of 3D systems unless we really need to go. And in this introductory course, we don't really, most of the time, need to go there. So thanks for listening me, and please join me in the last lecture on this chapter. So the final lecture soon we'll be focusing on the transport properties. So we want to understand next how these pieces of metals can actually conduct electricity inside them. So thanks for listening, and please stay tuned.